Thanks everybody for coming back for what turns out to be Scene 6, Loopage. But before we begin, I recently read a white paper, some guys comparing two application platforms, one written in C++ and one written in Java. And they sort of went through the features, comparing them and deciding, which of the platforms was better. And when they got to garbage collection, they said garbage collection is a programmer convenience. And then they evaluated the two systems based on how large a convenience it appeared to be. And so they measured the number of dispose instructions in the C++ code and found there wasn't a lot of that, and then determined that it was not a programmer convenience, which was completely wrong. That's not what garbage collection is. Garbage collection is a reliability mechanism. Having garbage collection, it means that you're not going to have dangling pointer errors and all these other hazards. And it also means that there's a large class of wonderful algorithms that you can consider that are really too dangerous to consider if you don't have garbage collection. So they completely screwed up their analysis. And basically their conclusion was, if you're into C++, you could feel good about not understanding Java. And that turns out to be a really bad way to think about things. You really should be making decisions based on good information and deep understanding, and very often that's not what we do. But that's not what I'm going to be talking about tonight. I'm going to be talking about loops. So here's a loop statement. You've got it says loop, and you've got a block, and as you would expect, all of the statements within the block will get repeated over and over and over until something happens. JavaScript doesn't have a statement that looks quite like that, which I think is a shame. I would like this to be in the language, or would have liked it to be in the language, for two reasons. One is the loop affordances that it provides expect you're going to always exit either at the top or the bottom of the loop. And I don't know if it's something weird about me, but I tend to exit out of the middle more often than I exit out of either end. And you can do that, you say while true, which just looks stupid. This is the more elemental thing. The other is that it makes it easier to think about the language. If this were the primitive loop statement and all the others were simply variations on that, then the language in its core would be smaller and easier to reason about. So when you're thinking about the language's security, you have less analysis to do, and I think that would be a useful thing. So, for example, we can take a while statement and desugar it into a simple loop statement. And you can see by the amount of desugaring it does, the while statement really isn't buying us very much. We can do a similar thing with the do while statement, and it's sort of interesting, while the do while looks very different than the while statement, what it does is actually almost identical. The only difference is that it put the test on one end rather than on the other. And then when you look at what the for statement actually does, it really doesn't do anything at all. It just is complicated. Now, another way that you could think about doing iteration, another way of doing a loop, would be to use recursion. So another way that we could have transformed the while statement would be to turn it into a function which calls itself and continues to call itself as long as the condition is true, with two restrictions. One is that because of the way functions work in JavaScript, you can't take any arbitrary code and put it inside of a body here. Arguments, this, break statements, and return statements, the meaning of all of those change when you put them into a function, so you can't put them in the body here. The other more important thing is that JavaScript does not implement tail recursion optimization, or what people call proper tail calls. So you can run for a while, and then it's going to start to slow down as it accumulates memory, and eventually it's going to fail. And you don't like it when programs fail. I'm hoping that maybe someday in the distant future, JavaScript would be enhanced to allow this, but it doesn't yet. But that's not the kind of loop that I'm here to talk about tonight. I'm here to talk about event loops, because event loops are much more interesting. Event loops are the heart of the web browser. Everything works in the web browser based on an event loop. So an event loop is driven off of an event queue, which contains callback functions. And those callback functions get put onto the queue by the timer using set timeout or set interval. or by the UI events, so clicks and mouse overs and all that stuff gets translated in and put into the stack or into the queue, and network activity. So when a script gets loaded or a loading is complete, that information will be put onto the event queue. Then the event queue takes turns. So in each turn, it takes one callback off of the event queue, runs it to completion, and then does the next one. It's a really simple loop, but it's a really powerful loop. The prime directive in an event-driven system is never block. So you can't wait for I/O, or you can't wait for network activity. You just run, and when you can't run anymore, you return. You can set up other things to run in the future, but you never block, you never wait, and you have to finish fast. If you can do those three things, you can run really well in an event loop, and that's how the browser runs, and the browser runs really well. The event loop is one of the best parts of the browser, but because it's a part of the browser, we didn't get it completely right. So there are a couple things in the browser API which block, and because they block, you really shouldn't use them. So Alert and its sisters are okay to use for debugging, but you should never put them in production code because they will block the main browser thread. Also, the XML HTTP request has two modes, a synchronous mode and an asynchronous mode. The synchronous mode blocks. Because it blocks, you should never use that. Fortunately, there is an asynchronous mode which does the right thing. It makes the request, and then you can have a callback engaged when it finishes. So in the browser, when UI events are generated, it's possible to have multiple event handlers run as a result of bubbling. But in reality, there's only one function that runs, and it's something that's similar to this one. It'll be a little bit more complicated. But it will end up looping through the DOM, looking for an event handler that says, okay, we're done processing this, and once it's finished, then that's the end of the turn. So that's how we do event delegation in JavaScript. So does anybody know who this lady is? Show of hands. Who knows who this is? Everybody should know who this is. This is a really important lady. This is Grace Murray Hopper. She was the first woman to get a PhD in mathematics at Yale, then went on to teach mathematics at Vassar. When the US entered World War II, her husband signed up and joined the military, as did her brother and her cousins. And she decided that she would too. So at the age of 36, she resigned her tenured position at Vassar and joined the Navy. Being a mathematician, she thought she'd probably be assigned to do cryptography or some other kind of code-breaking business. Instead, she was sent to Harvard to work for Lieutenant Commander Howard Aiken on the IBM Automatic Sequence Controlled Calculator, the Mark I. First thing she did there was essentially take the machine apart and figure out how it worked, because there was no documentation on what you needed to know in order to program the thing. So she had to figure it out. And she figured it out really well and then taught other people how to program the machine and spent the duration generating numbers for solving hard problems in ship design and weapons design, all driven by the need to get the country quickly to the end of hostilities so we could bring everybody home. When the war was finished, she ended up going to a computer manufacturing company, one of the world's first computer manufacturing companies, to work on the UNIVAC. And she quickly figured out something that everybody else had missed. The thinking was these machines were ridiculously expensive, and human life is very cheap. So it shouldn't be at all difficult to find enough people to write the programs for these machines. She realized that there are not enough people who are defective in the way that all of us are, that they could make a business out of selling UNIVACs. They just weren't going to be able to make enough software at the rate that they were making software at that time. So she thought we need to figure out a way to get smarter about developing software. So she wrote a program which she called A0. Just an indication of how far ahead she was as a programmer. She didn't call it A1. Okay? That's an important clue. A0 was the first compiler. The reason we call compilers compilers is because of Grace. Okay, she did this first. And what she did was she thought subroutines are going to be the unit of code reuse. We need to figure out a way to make it easier to reuse subroutines. So she put a big collection of subroutines onto a tape and gave each of the subroutines a number similar to a library book call number. And it looked a lot like the Library of Congress system. So all the trig functions started with T, for example. And so your program would be a list of subroutines, and A0 would scan through that tape and compile a program based on all of those things, compiling in the same sense as compiling a bibliography, that's why we call it that. If ever wonder why we call a function or call a subroutine, why does that call? Because it's nothing like a phone call. It came from this, the library metaphor, because she was an academic. She had two kinds of subroutines, open subroutines, which just get inserted into the program in place. Today we'd call that an include or an inline. And she had closed subroutines, which today we call functions. There'd only be one occurrence of those and some extra overhead in getting to it and back again. So in modern terms, A0 doesn't look much like a compiler. It looks more like a linker. But this was the first, and everything else grew from that. When she finished A0, she gave it to her team, and they built A1 and tested that and learned more, and then built A2. A2 was the first open source project, because A2 was given to Univac's customers. For the first time, customers were given source code to an interesting project, and they modified it and made suggestions and gave them back. And that helped to significantly improve the next A3 and going on. So open source is almost as old as computing. It's not quite as old, because it turned out open source didn't work unless you had multiple people with the same machine. And up until this point, all machines were one-offs. You'd build it usually as a research experiment, and you'd learn things doing that so that the next one you built was going to be very different. So Univac was the first time that people could share software across machines. A2 led to A3 and then to AT3, which eventually got renamed as Mathematic. And Mathematic is beginning to now look like a modern programming language. In fact, it looks quite a bit like Fortran, which was developed about at the same time. Huge advance in software development. And like all huge advances, it was rejected by some of the best programmers of the day, who contended that programming took too much creativity and dexterity, that you couldn't replace the human with a machine. It's just not right. It's not going to work. Turned out they were wrong, that they completely misunderstood what this series of tools were intended to do, not to replace them, but to help them be more productive. So one of the features of Mathematic and Fortran was read and write. And one characteristic of both of them in both of those systems is that they would stop the program while the I.O. was happening and then suspend the program until the I.O. was finished, and then they would resume. The thinking was that there's no reason to do anything else because the program was useless until it got the data it needed anyway. And it was also modeled after the way people were thinking about hardware at the time, that you've got a black box, and it's got an input, and it's got an output, and something that happens in the middle. So there's a symmetry between input and output. Later, we find that there's not a good reason to demand that symmetry, but at the time, we had it, and it was extremely influential. When we moved into time sharing, we took the same languages with us. We also invented some new ones, so we got BASIC, which was sort of a beginner's version of Fortran, but had basically the same model. So the problem with writing interactive programs in those sorts of languages is that the programs are highly modal, that the user can only type in what the program is expecting at any point, because each read statement is going to be different in its expectations of every other read statement, and the user doesn't get to choose which read statement is going to execute next. Now, it turned out this worked really well for time sharing because it depended on the blocking in order to allow it to have the appearance that it could be serving multiple people simultaneously. Because once one program was blocked, but others could run, and it turned out most users spent most of their time looking at the printout trying to figure out what to do next. So virtually all programming languages have blocking I/O, read and write in almost every programming language. There are a couple exceptions. Algol didn't specify I/O, and C was the big exception. It had no I/O at all, which was great because it meant that you could modify the environment that you're going to run C in to use any I/O model that you wanted. So it was going to be a great thing for doing experimentation, except that it came with standard I/O, and that's the one everybody used, so it might just as well have been built into the language. Everything blocks, which is a shame. So meanwhile, in some of our research laboratories in places like, say, SRI and Xerox PARC, people were experimenting with other models for how to do interactivity in programs. Also, we saw the invention of computer gaming. And the computer game authors pretty quickly realized that having read statements didn't work for most games, that you wanted a different way of organizing the program so that it could be more responsive. But the mainstream didn't see much of this until, say, 1984, when the Macintosh came out. The Macintosh was the first mainstream product that got in front of mainstream programmers with this radically new idea of how to do interactive programs, which was not based on read, but on event loops, a radically different way of writing programs. And so were the programmers happy to have this new model? No, they were quite unhappy. You have to write programs inside out. Wow, nobody can do that. It's too hard. It's just not the way God intended us to write programs. We should go back to the command line as he intended. So Apple had to work really hard to try to convince programmers, no, really, it's okay. You can be successful writing in this model. They released a program called Mac App, which was a template of a Pascal program that already came with an event loop built into it with prototypes for setting up menus and things like that. So all you had to do was hook your logic into it. And that was just too hard. It was rejected. So that it looked like Macintosh was not going to be the big success that it turned out to be, except for one thing, HyperCard. Bill Atkinson had this little multi-layer paint program with a silly little scripting language in it, and suddenly everything took off because non-programmers could be incredibly productive with HyperCard. They could get a stack, that's what they called programs at that time, and they could open it up and look at the scripts inside of it and fiddle with them and make wonderful things happen. And in fact, there were thousands of stacks running around the world, most of them being written by people who had no business programming, just because it was fun and easy. So after that, the professionals kind of went, oh, okay, I guess it's not that hard. We could probably do that. And then we saw an explosion of programs for the Macintosh and Windows, where a new generation of programmers were finally able to work with the event loop. So HyperCard worked because it was all about events. You didn't have to build an event loop. It was built in. It just worked. So all you had to write were the event handlers. So a program, again, a stack, was just a collection of event handlers attached to things like cards and buttons and fields. And the events could bubble up. That's how it did delegation. They called it inheritance, but it really wasn't inheritance. So it had events like on mouse up and on key down, on card enter, which would be equivalent, say, to on load today, and on idle. On idle got fired whenever the event queue was empty. And I don't think they knew what people were going to use that for. It turned out they used it for animation. So if you wanted to move something over and over again, you would do it on idle, which worked for that generation. But when the next generation of Macintoshes came out that were faster, suddenly all the animation went crazy and didn't work very well. So the lesson from that was, if you don't provide a right way to do something, the street will figure out its own way. It turns out the browser learned from that, and so we've got set interval, which was a correct response to this problem. So HyperCard had a huge impact on the evolution of the browser. Basically, the Netscape 2 browser was an attempt to put HyperCard functionality into the browser. And not surprisingly, JavaScript is well suited to this model. Not surprisingly, because JavaScript was invented specifically to do this. And in fact, it does it really well. So as awful as the DOM is, JavaScript with the DOM is an effective programming environment. You can actually get stuff done. And if you put on top of the DOM an AJAX library, say a good one like YUI3, it's even better. It's way better. So one of the ways we're blessed here is that JavaScript does not have read. It does not ordinarily break or halt. And that's a good thing. It's always been seen over its lifetime as a huge deficit. JavaScript is bad because it can't read. But it turns out that we're actually better off for it because it's easier for us to think about event loops than people coming from other languages. It turns out you can do an event loop in any language. But we're better at it in JavaScript because we've never had this two-mind thing where sometimes you block and sometimes you don't. Being in a world where you never block just makes life easier. So read is bad because it blocks, and blocking is bad for event loops, and that's where we live in the browser. And so JavaScript programmers are just smarter about using event loops than programmers in other languages. It's just a fact. You guys are just smarter. So event loop is just one approach to concurrency. There are lots of others. The most popular approach today is threading. So everything has trade-offs. Everything has pros and cons. So these are some of the pros and cons of threading. Well, first off, everybody knows what threading is, right? I don't have to define that. Right. So the first pro, and it's a huge one, is no rethinking is necessary. Anytime you come up with something and say, and you don't have to rethink, it's like, great, sign me up. I'm ready to do that. I'm ready to not have to think. So all of your bad habits work just fine under threading. Programs can block. It's not sensitive to blockage the way that event loops are. In fact, it loves to block. The whole reason to have threads is so that they can block. And execution will continue as long as any thread is not blocked. And if you have multiple cores, and if they're not blocking each other, they can all go forward, and that's a good thing. Maybe your program will go faster if you're lucky. There are some cons. One is that you need to allocate stack memory per thread. That was once a big deal. It's not a big deal now. Memory is so cheap and abundant. A real concern, though, is if two threads are using the same memory, a race may occur. Which is even worse than saying a race will occur. And I'll show you what I mean by that in a moment. And there are more cons, but before we do that, for years people have been saying, why can't we have threads in JavaScript? So let me show you what happens when you have threads in JavaScript. Here we've got two one-line programs, which are each going to run as a thread, both at the same time. And they both are sharing access to my array. And each are going to append one element to my array. There are several possible outcomes of this. One of them is that we get an array containing A and B. Another is that we can get an array containing B and A. This is not the race I'm talking about, although you do have this non-determinism, and that's considered good. Okay, let me show you what's considered bad. One possible outcome is we get just A or just B, even though both successfully completed their writes. Now, how is that possible? Anybody have a question as to how this went wrong? Okay, so let me show you what went wrong. So one way you can look at appending something to an array is to break it down into several more primitive instructions. So when you do that first statement, you're doing the equivalent of the last four statements. Everybody see how that works? Okay, now when you have threads, they're both doing similar stuff, and they can shuffle the order of the execution of this stuff in any way that they want. They might do it always the same way, or they might occasionally do it a different way. The way they'll usually do it is they'll work fine when you're in development and do it in a really bad way when you're in production. Or they'll do it a really good way until the investors come, and then they do it the bad way. So what actually happened in this case, the way we got to B, was they both went after the length at the same time. And so they both ended up wanting to store the value into the same cell. So the one that went last won the race. This is really bad. There's no integrity in this program now. And this is the kind of bug that's really impossible to find because you can look at the source and you can't see any way that says, what happened to A? I can see the statement A went into there. Very few people are able to think in the multidimensional way you need to be able to work this out. So it's impossible to have application integrity when you're subject to race conditions. So you have to prevent the races from happening. Unfortunately, there are mechanisms for doing that. It's called mutual exclusion. And there are several famous techniques which are all somewhat equivalent. Some have better expressive capabilities than others, but they all do the same thing, which is to try to prevent two threads from getting at the same memory at the same time and causing this kind of problem. This used to be operating system stuff, but unfortunately it has leaked into applications because of networking, because now you need to be able to go off to some place where you may have to wait a long time before you can get a response back, and also because of the multi-core problem, that we don't know how to make CPUs go faster anymore. So the way we go faster is by having more of them, which turns it from a hardware problem, which is what it should have been, into a software problem. And so now, in order to make your application go faster, your application has to take advantage of threads. And nobody knows how to do that well, particularly at the application level. So under mutual exclusion, only one thread can be executing a critical section at a time, and all the other threads that are waiting on that section are blocked and cannot proceed until it's released. Now, if threads don't interact, then the program runs at full speed and everything's great. But if they do interact, then races will occur unless mutual exclusion is employed. But there is another problem that comes from that, and that's deadlock. So here we have Gaston and Alphonse, two threads, who are both employing the same mechanism, which is, I will go after he does. And so neither can go, and so they're deadlocked. It turns out this is a remarkably easy thing to do when you're dealing with threads. Deadlock occurs when threads are waiting on each other, and races and deadlocks are just really difficult to reason about. There are very few people in the world who can reason about them effectively. My belief, and I mean this sincerely, is that they should all be enslaved and made to work on operating systems. And that nobody else should have to go near with this stuff because it's just way too complicated. These are the most difficult problems in software development to identify, debug, and correct. Managing sequential logic, which is what we do, is really hard. And managing multidimensional temporal logic is really, really hard. And you should not be doing it at the application level. It's just wrong. So getting back to our con list, turns out there's overhead in dealing with threads, that getting a lock is surprisingly expensive. Deadlock is a constant threat, that a program which does not deadlock can be transformed into a program that does deadlock with extreme simplicity. It's really easy to break a program and allow it to lock up. It's just incredibly difficult to think about. And in my opinion, the most tragic design error in Java was that it couldn't make up its mind if it wanted to be an application language or a system language. And so in trying to do both, it exposed threads to the application developer, and that was terrible. Fortunately, though, there is a model that completely avoids the reliability hazards of threads. And that model is the event loop. Hooray. So here we go back again to the event loop. So nothing's for free, so there are some trade-offs. So let's look at them again. So on the pro side, we can be completely free of races and deadlocks, which is a huge win. And for application developers, that's the world you want to be living in. In terms of memory allocation, there's only one stack, which it gets shared over and over and over again. Again, that's not a big deal, but it's sort of nice. For example, at the end of every turn, the stack gets reset. And so getting machine clean after something goes wrong turns out to be really easy. We have very low overhead because we're not blocking all the time and we're not doing process switching, which can be expensive. It's just running through the event loop, which is a really efficient thing. We also get some resiliency. So if a turn fails, generally the program can still keep going. Whereas if a thread fails, there is a possibility that that thread was holding on to a lock that, or that another thread was waiting on it completing some action that will never get completed, and so you can get cascading of thread failures. That doesn't happen because in event loop because we don't have that kind of dependency. On the con side, again, programs must never block. Programs have to be written inside out, wah, but that's not hard if you're a JavaScript programmer because that's how we've always done things. And turns must be finished quickly. So this is the most important con. So it means that event loops are not suitable for all programs because some programs need to take a long time to run, and anything that takes a long time to run cannot be put into an event loop. Despite that, there are a couple of things that we can do. One is we can employ iteration. Iteration means to break a task into multiple turns so that on each iteration, instead of going through a conventional loop, at the bottom of the loop, we call set timeout, passing it a function which causes us to do the next iteration. So that means that the turns are going to be short, the turns only as long as one iteration, and we can do as many iterations as we want and not lock up the event loop. The other thing we can do is we can move the task into a completely separate process. And this is a thing that Google showed us with Google Gears, which is brilliant. So you can take another process, put your program in it, and it will send an event back to your event loop when it's finished. That's brilliant. We can even take that further. There's no reason why that process needs to be on the same machine. It could be on another machine. It could be anywhere in the world. It could be closer to the data rather than to us, if that turns out to be the most effective place to put it. Another way people think about doing this stuff is the remote procedure call, which combines two great ideas, functions and networking, producing a really bad idea. So like read, it attempts to isolate programs from time. There was a long time when that was thought to be a good thing, but when you're doing highly interactive programs, especially programs that deal with people, it turns out to be a really bad thing because the program blacks out. It experiences lost time, and it's not aware that it blocks out. And reading the program, it is by design difficult to see where the time is lost because remote procedure call is a deception. It's intended to disguise the fact that you're going across the network by making everything to appear to be nice, local, fast calls. And so all of this can result in a terrible experience for the user because lost time turns into annoying delays, and people don't like that. It's rude and it's disrespectful. It's not a good way to treat people. So what we need to do instead is to give people the best feedback possible. And latency compensation is an important technique in doing that. So at a minimum, we need to immediately acknowledge the user's input. If the user clicked or entered something, we need to let them know right away, got it, we know what you're doing, we're on the case. We don't want to lock up the interaction while we're waiting for the server's response. We want to keep everything dynamic. In some applications, we can actually do better than that. If we can predict what the server's response is going to be, we can go ahead and put that on the screen. And if it turns out we predicted wrong, then when the server tells us so, we can then correct it. But for a lot of applications, that can make an extremely nice experience for the user. So let's talk about security. Security is a really important thing. And we saw when you're trying to write applications using threads, security really isn't attainable because you don't have consistency, and without consistency you can't reason about the correctness of your program. Correctness is virtually impossible. At least it is for me in that environment. So we do better in an event-driven system than in a threaded system. But just having threads or just avoiding threads doesn't guarantee that you're going to be secure either. For example, the browser today is a nice event-driven system, which is good, but we've got this terrible problem that we call the cross-site scripting problem, which is terribly named because the name suggests that there's something wrong with cross-site scripting, and there's not. Cross-site scripting is extremely desirable and valuable. It's how we do mashups, and mashups are good, and we want to be doing more of that. The problem is that the browser's security model didn't anticipate that we were going to do that, and that's bad and needs to be corrected. So if you look at what causes this problem, there are two basic causes, and it's pretty simple. The first is the sharing of the global object. So any script that can get onto the page anyhow gets access to everything that that page knows. So they all get into everything. Now we're improving that in ECMAScript 5. ECMAScript 5 has a strict mode which will allow us to put third-party code on a page and be confident that that third-party code cannot do all the bad things that happen in cross-site scripting attacks. That's a wonderful thing. So hooray for ECMAScript 5. I just can't wait until Microsoft and all the other guys get it out so that we can get on with the future. The other problem, though, is inherent in HTML, and that's HTML is just way too complicated, particularly in that it has nesting of multiple languages, including CSS and URLs and JavaScript, which can all be nested inside of each other, that all have different encoding patterns and different escapement patterns. And so it's extremely difficult to do static analysis on a piece of code and determine if it's going to be safe in any context in which it might be put onto the page. So both of these things need to be corrected in HTML. We cannot fix them on the ECMAScript side. Tragically, HTML5 ignores and worsens the XSS problem. It does nothing to make it better and does a few things which will make it significantly worse. The editor of the HTML5 recommendation has written that HTML does not ever have a markup injection vulnerability. So that working group simply doesn't understand the problem that you guys are living with every day, and so they're not at all motivated to try to correct it. I think that's intolerable, but that's the situation. So what you have in the browser is a loaded gun pointed at your head, and this pulls the trigger. So we tend to use page templating languages, PHP, ASP, JSP, which made a lot of sense in 1995 when Rasmus did PHP. That was a really good idea then. It's not so good now. Templates are way too rigid a framework for the kinds of really dynamic pages that we're trying to build. But worse than that, it's way too easy to insert text into a context that gets delivered as part of the HTML load, which can be misinterpreted and executed, completing an XSS attack. So could we do better if we had JavaScript on the server? There are some obvious advantages. One is that all of the expertise that you've gained in doing JavaScript can be applied immediately to the server. That's got some huge benefits. Turns out this is not a new idea. The first server-side JavaScript implementation was from Netscape in 1996. Unfortunately, they modeled it after PHP. Syntactically, it was a little different. They had a server tag, which resembled their script tag, which caused stuff to run on the server. And they had a write function, which would cause the insertion of whatever text you were writing into the HTML output stream. So it had all of the vulnerabilities that PHP has. So it had all of the disadvantages of the other template systems, plus, at the time, a pretty slow JavaScript engine. So that product was eventually withdrawn and replaced with J2EE. So what if we did it right instead this time? We have one of those opportunities in history where we can try it again and this time get it right. So what if we had server-side JavaScript with an event loop? Not a template system, but event loop. Well, it turns out we've got it. We already have it. It's Node.js, which runs on top of V8, and it implements a web server in a JavaScript event loop. And it's brilliant. It is a very high-performance event pump. It can take events and move them really fast through its event queue, in and out, and across the world. Not only that, it got read right. So here's the file system read from Node.js, and it has a callback function. And the callback function receives the data that you asked to read. I mean, that's right. I mean, we finally have a correctly implemented, correctly designed read function. So everything in the Node.js API is non-blocking, or should have been. There are a couple exceptions. One is he has some synchronous functions which do block, and that's really unfortunate. I wish they weren't there. There are non-blocking versions for most of them. There shouldn't be any. It's just too big a hazard. And the other is there's a require function which blocks, which is used for loading script. That's really unfortunate. I'd like to see that fixed too. But otherwise, Node.js is just really good stuff. So There are a lot of advantages that come from it. One is that you can run the same stuff on both sides of the network. So we can take YUI, the same YUI that you're running in the browser, run it in the server. So that means your applications can run on either side. So maybe you want to do the initial page load on the server side so you can send HTML of the first view so that the user can be looking at that while you're sending the rest of the scripts over. You can do that now trivially. It used to be you had to write the program twice in order to have the two views. Now you only have to do that once. If you want to have a web service which provides a portion of that view so that it can be included in other programs, that web service can be created with the same program. We've got other advantages too. We can take advantage of YUI's connection manager to go off to several services simultaneously to get additional material that we want to put onto the page. That all happens asynchronously. So the time cost we spent on that is the max of all of the services that we go out and read. Whereas if you're doing it in PHP, you pay for the sum of the time of all of those services, which can be significantly bigger. Now in PHP, you can do it asynchronously, but it's hard. And nobody wants to do hard in PHP. That's madness. That's not what it's for. But in JavaScript on YUI in Node, it's easy and it's wonderful. So it's a huge advantage. Also, we're running on V8, which is Google's JavaScript engine, which is a very nice engine. Comes out of the Self tradition, which is really smart stuff. It observes the program as it's interpreting it, and if it sees patterns of recurrence, then it goes, okay, I think I know what's going on. I will compile it and make that little bit of code faster. So it starts finding sequences in the code that it can make fast, and eventually your program is going really, really fast. Now, V8 is also available in the Chrome browser, and it's not as effective there because you tend not to spend that much time on running a program on any page. But in the server, you're running there all day, so there's a good opportunity for it to learn about your program and speed it up. So this is a really wonderful configuration. Now, if you look at the stack of protocols that we have to work with, we got the wonderful IP, which can move a packet pretty much from any place in the world, any other place. That's a wonderful thing. We got TCP that runs on top of it that makes it reliable and provides for sequencing. That's a really good thing. Then we've got HTTP, which is just completely wrong. It was designed for a time when the web was a static document retrieval system. And it's fine for that, but that's not what we do now. We're not retrieving static documents. We've got highly interactive applications going over this channel. And so the fact that HTTP is stateless becomes a real problem. And so we spend a lot of time in working our AJAX stuff trying to put the state back in, and it's hard. It'd be nice if we could just get rid of HTTP completely and run AJAX on top of TCP, which would be really clean and elegant and performant and wonderful. I don't think that'll ever happen because there's so much arthritis that's found its way into the internet now. All these nodes out in the network that will only allow HTTP through, so that really the only value in HTTP now is for funneling, because that's the only thing that can get through the firewalls and the proxy servers. It's stupid, but that's the world we live in. It's a stupid world. So let's go back to the beginning. Okay, the very first browser and the very first server, initially they were both on the same machine. Eventually they figured out how to put a wire between them, and that was a good thing. That's when it started to get interesting. Now, pretty quickly you get to the point where you've got so many browsers trying to attack one server that one server can't do it anymore. So we had to start thinking about how are we going to scale. So historically what we did was we'd put a distributor in front of the servers, and so each request that comes in, it can route either at random or round robin or least loaded, whatever policy you want. The message goes somewhere else and that server deals with it. And then you've got a database in the back that they can all share. So the database becomes a problem, so that becomes a bottleneck. And initially everybody was using some kind of relational database there, which I think was a really bad fit for this. And the relational database was developed at IBM back in the mainframe era to solve a completely different class of problems than we have here. But there were a lot of people who understood how they worked, and understanding how they work means you don't have to rethink anything, so great, we'll just take that and put it in. And they didn't scale. So in the decade since then, we've done a lot of things, figuring out how to shard them and do other stuff. And in doing that, you break the relational model. So most of the goodness that you got from that model you don't get anymore, but at least you don't have to rethink anything. Okay, so life continues. But at some point, even that doesn't work, and so you start looking for other options. And so people have come up with NoSQL databases, which are wonderful. I love these things. So there's like Mongo and Couch and all the others. They're great, where people are kind of going back and changing the assumptions and going, what's really important here? And the important thing often is scalability, and you're willing to trade off a lot of other things in order to get that, and we're getting it, and that's really good. It turns out Yahoo's been doing this for a long time. We had a massive homegrown NoSQL database in production here since 1996. So we've been doing this for a long time too. It's wonderful stuff. But now let's put Ajax on top of all of this. And this model was not designed for Ajax. This is something that we kind of figured out after the fact that we could do. And it's not optimal for us. And the biggest problem is, where does the server put its state? Because this whole model assumes that it's stateless, so that any request can go to any server. So it means you can't keep the information in the server. You've got to keep it somewhere else. And so one place where people put it is on the wire. So you put it in the cookies, or you put it in headers, or you put it in secret fields or in URLs. So you're passing all of that information back and forth all the time, which is really inefficient. And some people got tired of that and said, okay, well, let's just put it in the database. And that's an awful place to put it. That's like the worst possible place in the universe to be putting your ephemeral state. I mean, that's just not where you want to do it. But you don't have anywhere else. Fortunately, there is an alternative. There's a system called Elko that was developed by Chip Morningstar, which is all about maintaining session in these servers. And he's got a device called a session server. And you initially connect to the session server, and the session server will determine, okay, we'll use one of these servers for your session. And it'll tell you about it, and it'll tell the server about that. And from that point on, the browser and that particular server have a connection that they preserve through the life of the session. And the wonderful thing about that is, where does the ephemeral state now go? It goes in JavaScript variables that are closed over the event handlers that are in the event queue in the server. They are in the best place in the universe, where there's absolutely no cost at getting that information and making it available to the application. See, you add that to the Node.js now, and the amount of work that you have to do in order to do a stepwise increment in the Ajax application starts to get really, really small. So we've got some really wonderful stuff now happening in server architecture because of opportunities afforded to us by JavaScript. So a final thought. A little while ago, I was talking to a friend of mine, really bright guy, one of the smartest programmers I know, about what we should do next with JavaScript. And I suggested to him that we should get the tail recursion thing going. We should get that fixed. And why do we want to do that? And I said, well, because it would allow us, or among a lot of other things, it would allow us to do continuation style passing. I think that would be a useful option for us to be able to provide within the language. And if we don't optimize the tail calls, then we don't get that. And his answer was, I've never used continuation passing, so I really don't see the value of it. Which I immediately recognized as a really stupid answer. And the way I was able to recognize it so fast is that I have used that same argument myself. And I've been hearing that same argument through my entire career. And basically, the core of that argument is, I'm not qualified to make a decision about that the onus is on you to educate me deeply about this thing that I'm not even interested in. So there's no way to overcome that kind of a requirement. Nobody can win that argument. But it turns out, usually that reasoning is wrong. So I've heard that argument about why we shouldn't have to worry about closure. I've heard about why we shouldn't use recursion. I've heard about why punch cards are better than time sharing. You can go all the way back to, It is better for us to be programming with digits. I don't understand why we need compilers. It's been going on from the beginning, and that's why software development is so slow, because basically we have to wait for a generation to die off before we can get critical mass on the next good idea. So this is Grace again. So see the courtesy WGBH, I had to pay $200 to get the rights to use this picture. It's actually $100, but I wanted lifetime rights, so I can use it from now on. So I'm going to use it a lot, anytime I can. So I used it twice tonight, so that's $100 a view. So I'm getting it down. I'm getting it down. So Grace, we've gone a long way since Grace created the discipline of software engineering. But we still have a very long way to go. And I think we're not as far along as we should be at this point. And I think it's mainly we're not farther along because of that I don't want to have to learn anything problem. You are not those guys, and that's why you're here tonight, to hear me rant about this. And I appreciate that, and I think that shows a lot of value for you. The big surprise for me in this is we're about to take maybe the most important step we've ever taken in terms of the technology of the web, and JavaScript is leading the way. Who would ever imagine that? JavaScript is now being the technology leader. It's not just the thing that we tolerate. Wow. But there we are. That's where we're going. So good night, Grace, wherever you are. And good night. Thank you very much.